part of the big aircraft design capstone for 2017, and I'm on the aerodynamics configuration and aerodynamics teams.
My name is Elisha Karich, and I'm the flight dynamics lead, and I'm also part of the aerodynamics.
I'm Alexis Houle. I'm part of the project management team as well as the propulsion integration team.
I'm Jacob Wagner, and I'm one of the team leads.
All right, and I'll be sure to talk as loud as I can, but just let me know if you have trouble hearing. So, an introduction to our project this year is a little bit different than years past. Rather than going to an entirely new supersonic aircraft, we have decided to take the 2016 RUAV design and improve upon it and hopefully gain a better understanding of low-speed flight characteristics for supersonic aircraft. So, in short, some of the things we're working on, we are taking the 2016 RUAV, we're improving the aerodynamics, and we hope to include things such as movable landing gear and movable leading edge devices. And we are also this year as a new component taking the RUAV design and also scaling it up to see what would the performance be if this were a true X-plane supersonic trainer aircraft. So the motivation and impact for this project, low boom supersonic configurations, that's one of the big limiting factors of supersonic aircraft nowadays due to regulations preventing supersonic booms over the continental United States. And so we're hoping to look a little bit into that, gain a better understanding of what constitutes a low boom supersonic aircraft. And we are also looking to aim to better understand the compromise between high speed and low speed aerodynamics. For example, a configuration that does well into the supersonic regime does poor into the low speed regime. For example, supersonics require low wingspan, high sweep, but in the subsonic regime we need the exact opposite. And on top of that, as you would expect for any aircraft design, we're looking to improve the structural design to allow for lower weight, higher structural integrity, ease of construction, as well as ease of repair as we go through our testing process. So some of the specifications that we're aiming to hit with this supersonic RUAV, at the model scale, we want to have retractable landing gear, as well as movable leading edges. And on top of that, one of the big areas that the 2016 aircraft was not able to meet was the one engine inoperable climb performance. So one of the big areas of our concern and one of the big areas of our analysis is going to be improving OEI conditions and aiming for a greater than 2% climb gradient. And at the full scale, for our full scale concept, some of the areas we need to hit are a 7,000 foot takeoff fuel length. In addition, we're looking at an approach speed of not to exceed 150 knots. Additionally, a minimum cruise altitude of 41,000, though ideally we're trying to hit about 50,000. And additionally, the idea is to have endurance of 45 minutes of super cruise at Mach 1.6, which is approximately 750 nautical miles.
So one of our main deliverables this year is going to be to actually retrieve some flight test data for our model, since a couple of the last year models did not reach that point in the project where they could actually gather data from flight tests. We're starting from gathering quantitative data such as CFD, wind tunnel data, and structural FEA analysis using industry standard analysis tools such as STAR CCM, NXT, and ASTRAC. We also want to make it a system of checks and balances so that during the iterative design process we have several doors we can go through to check and see if our data is reliable. For the RUAV scale model, we want to make sure that it is fully instrumented and airworthy upon flight test so that it can actually fly and we can actually retrieve data from it. We also want to make sure that it is manufactured to specs, because if it is not, then we cannot match data between our CFD analysis or wind tunnel data and flight test data to correlate the two. Since we don't have enough money to build an actual full-scale X-plane, we're just going to be doing mission profile analysis and performance analysis to make sure that it falls within the specs that we want, that Kelsey was talking about earlier.
So I'm going to give you a brief overview of our budget, schedule, and risks. For a project of this size, eye chart, the construction is the largest portion of our budget. That will include all of our molds and raw materials in order to construct the new UAV. In addition to that, the rest of the budget will cover any electronics, wiring, or equipment to make the plane fly in the end. Our schedule as of right now, we are currently in the initial design phases. We hope to freeze the lines of the tails and the fuselage by the end of week 7 this quarter, and the wings by the end of week 8. We will continue using the last couple weeks of winter quarter in order to create mock-ups and analyze our designs to make sure that we can construct what we have designed. We then hope that construction will begin the first week of spring quarter, with the wind tunnel testing being completed during week 3. So by this time, the 2016 wind tunnel model will be modified and completed, ready for wind tunnel tests. And finally, we hope to flight test by week 8 of spring quarter. And then the last few weeks of spring quarter will be used to analyze our flight test data, as well as compare that data to what it would look like on the full-scale model. With a project this size, there are some inherent risks. So the top 3 that we are anticipating are falling behind on our construction schedule. We are currently mitigating that by having our construction team sit in during our design team meetings in order to ensure that our designs can be constructed. Additionally, we are making sure that we have mock-ups completed before we start actual construction. Our second risk is delays due to learning software tools. We're already mitigating this risk by bringing in industry professionals to help our teams learn how to use these different software tools, as well as helping us to understand what is good data. And finally, unexpected costs. Last year, the largest unexpected cost came from construction, and this was due to not having proper understanding of the construction methods. So that's another one of the things that we will be mitigating by learning proper construction methods before we actually begin our construction. I'm gonna turn it over to Jacob to talk about our design.
Alright, thank you. Alright, so I'm just gonna walk you guys through really quickly our development approach and things we're gonna change relative to the 2016. So we've got a whole repository of data from previous years, wind tunnel tests and some old flight test data that we're using, building on the lessons that they learned and the configuration challenges that they encountered during wind tunnel testing to build up our configuration. We have a whole slew of analysis tools, from rough handbook methods and hand calcs all the way up to using full NS codes. We'll be using our previous models as test beds for different avionics, actuation methods, electronics, and construction methods. And we've got lots of industry advisors to help us anytime we get stuck, and to continuously monitor us to make sure we don't go too far down the wrong path. Give us lots of good advice. So now we'll just do a quick walk around of our configuration here. So starting with the aft fuselage, the things that we're going to change are the sponson integration. Currently, there are a lot of discontinuous load paths. The structure just wasn't exactly designed to support the aero loads there, so it'll be pretty much a complete redesign of the sponson and aft deck integration. The sponsons also were not exactly sized for the torque of servos needed to actuate the stabilators. So we'll need to think of a new construction method in order to access those properly. And our nacelles will also be based on our full-scale engine choice, which right now is looking like a GE 404 or a Rolls-Royce Spey. And we'll be designing our model scale nacelles off of that. And our model scale engines are still TBD. We'll probably pick those in the next week or so. For the tails, 2016 had a large directional stability problem, so we're changing our tail sizing accordingly to meet those requirements. Handbook methods and CFD both. And have to pass those aero loads and sizes along to our structures team to develop proper design. And we'll also be moving the landing gear further aft based on our wind tunnel data from last year, which will require reevaluation of our rotation power with the elevators. The wings are probably going to be our biggest change. We need to incorporate some aerodynamically sealed leading edge devices. In order to do that, we'll need to push the main spar back to give us some integration room. And the main landing gear position is going to change. Also need to completely redesign the landing gear box to ensure proper load paths. And our outboard wing is pretty much our main knob we're going to be twisting to improve our OEI climb performance. Probably will result in an increase in span and a possible unsweeping to improve that climb gradient. And then the forward fuselage, 2016's design was not for an X-plane, so they did not include a cockpit. So we are including one, which also so far looks to be improving our area ruling for volumetric drag. Improved canard positioning and actuation, and some slight rejiggering of our bulkhead positions for integration reasons. So overall, we're looking at the same target max gross weight of 36 pounds with at least 22 pounds of thrust at sea level, which was last year. All over, we're going to evaluate a complete structural redesign to ensure continuous load paths, beams everywhere designed for wiring and piping integration, and reduce our parts count and weight so that we have a simple model that can be easily constructed in the time constraints and won't have a weight runaway after construction is done. All right.
So any questions for this team? You have 10 minutes for questions.
There was, back on your first slide, there was a list of requirements, like 7,000 foot takeoff, field length, et cetera. Where did the requirements come from?
Those are our project requirements set forward by Chet and Ellie. It's just our.
So they're just gifted to you, essentially?
Yeah, essentially, because like we said, we're trying to hit the performance specs of what a comparable X-plane would be. And so we were given a theoretical RFP, a request for a proposal, saying that here's, if they were a theoretical company and they wanted a plane, here's the specs that they would want to meet, and they're all based off of what other planes in the same category are capable of doing.
Question by Professor Noel.
What software are you trying to learn here, or what software do you have access to that you need extra training on?
Well, a lot of this software, or all of the software, we didn't really have any experience in class with, so it was more, we structured the teams so that the people, for example, the aerodynamics already had previous experience with, for example, Star CCM or NX, so that not a lot of relearning was required. For example, for flight dynamics, VLAero is not a very complicated software to use, so we have a couple people trying it out and learning it on the go, because we do want to make it a learning process in the end as well.
Somebody at the back there?
Yeah. Could you comment on what the current state of the project is? It sounds like you have a lot of scheduling risks. So did the previous project not get fully completed, and where is that at?
So it looks like right now we're going to be a couple of weeks ahead of schedule compared to last year. And with all of us working to construct it after lines are frozen and the wind tunnel test is over,
Right, but
it looks like we're coming out ahead of schedule.
But the question was about where did last year leave you? Like, what are you picking up from last year? I wasn't particularly clear on, like, is there a fully completed model that flies, or what's the...
So the model's completely constructed, and maybe somebody on flight test in the audience can give more specifications. So one of the things we're additionally doing on top of improving the 2016 planes, we're also completing the 2015 and 2016 planes with the intent of making them flyable. And because we're fortunate to be iterating on an already existing configuration, we have the benefit of seeing lessons learned from that, being able to improve our scheduling, improve our efficiency per se, to make sure we don't make the same mistakes that caused the 2015 and 2016 planes to not fly.
Yes.
You mentioned that it is obviously going to be a scale model. What is the scaling that you're anticipating for this?
Looks like right now a scale factor of 10 would well exceed our performance requirements. A scale factor of 9 would be pretty close to cutting the edge, so probably somewhere in between, or we might just go for a 10 and design a much better X-plane that is more of a demonstrator, technology demonstrator testing with the actual airplane once it is done. And there's also, we are gonna run X-plane simulations, so you can run virtual flight tests and get pretty decent dynamic derivatives. Does anyone in flight test wanna talk about
Yeah, so I'm the flight test lead for this project. So kind of like what was mentioned, the 2015 aircraft was pretty close to being done. And so some of the data we're trying to get out of that is like kind of like what Jacob mentioned, control, stability and control kind of stuff. So we'll like pulse the stabilators and see how the aircraft responds. You can also get like airspeed data and with angle of attack, you can get a lot of just like control and like how stable the aircraft is and how it responds to certain inputs, so it doesn't fall out of the sky if something happens.
So most of this is gonna be simulation, not actual model flying.
there will be model flying this year.
Other questions? Remember, this is a large group project, so there are more than 4 people, right? So there are leads in the audience, you can ask questions. Yes, go ahead.
So with the construction, I know that in the years past, a lot of times, the actual construction of the model would be done by like, not necessarily the students, but a company that specializes in building models, or, some parts of that were done like that. The construction that you have here, is this all being built here at the UW? Or?
Our wind tunnel model is not built by us.
Okay.
But our actual model is. Austin, maybe do you wanna?
Yeah, I don't know if we get to see the model in the.
Mostly when you can stand up.
So we have the 2015 and 16 in the Kirsten Wind Tunnel right now. Those were both constructed in-house. All the layups and everything are all done in the Kirsten Wind Tunnel. We also do for the spars, ribs, all the internals were water jetted on campus as well. So yeah, it'll all be done here. Besides the wind tunnel model.
Just worth noting with the wind tunnel model, it's a significant cost, upwards of $50,000. It's graciously donated, but this year because we're doing a derivative design, a lot of that cost will be present, and we can instead just do small modifications here and buildings to fail to see fit.
Yes.
So you guys talk about the model engines that related to industrial engines, and you want to have a scale down. How do you specify a model engine that is similar to the real industrial engine at the thrust curve?
So with a jet, your thrust curve is pretty constant at these low speeds, but in terms of thrust over weight scaling, that's something we try to match the Titanic.
Do you do anything with the response time?
I'm not sure specifically about response time. Most of our like stability control data is the transient behavior of the engine is not particularly important. But if anyone on propulsion has anything to say about response, our propulsion data isn't here, but it's not something that's particularly clever.
That's not good. Why is the question not here? Sounds very simple.
I'm not sure. I think he had a pre-listing of it.
Oh. You're taking attendance, right?
This paper's taken.
Very question.
How accurate do you think your model's gonna be towards like indication of that, like how a full scale plane is, like I know you're not making a full plane, but do you think your model will be very accurate, representative of how a full scale model or a full scale plane would act, or is this just like this is kind of how it's gonna look?
You mean during or?
Yeah, like performance.
Yeah, so it's a little bit in the weeds here, but the data you can get is good if you can scale everything properly. But when you like look at a video or if you're watching a model airplane flying, it looks like things are happening faster than they would in a real airplane. So there's different ways you can scale the weight in order to get like a dynamic scaling if you're after dynamic transient behaviors or code style, like flight dynamics don't matter, we just wanna make it look right. If you scale it dynamically so that your dynamic behavior is the same, it actually won't look visually like what you're expecting. So again, kinda in the weeds, but the data that we get will be accurate, even if I know it doesn't look like it's behaving quite like a real plane, because that's not what the way that we scale it.
Okay, great, thanks. We gotta move on to the next group. Thank you very much.